I would like to begin in the early 1700s with a remarkable woman named Émilie du Châtelet. Émilie was born in 1706, and she was the only daughter of a wealthy and connected French family. She was brilliant at mathematics and languages from an early age. Her father lamented, quote, "My youngest flaunts her mind and frightens away all the suitors. We just don't know what to do with her." Her father was exaggerating, of course, because with beauty, money, and high social status, there were plenty of men who were willing to look past her unusual intelligence. When she turned 18, she decided she didn't want to be forced to live in a convent, like most unmarried upper-class women were at the time, and agreed to an arranged marriage to a 34-year-old marquis. They had 3 children in quick succession, and afterwards had what can only be described as an open marriage. In 1733, Émilie met the poet Voltaire, and they immediately fell in love. Voltaire was always in trouble with the French government for pushing for freedom of religion and speech and satirizing the religious and secular leaders of the day. In fact, when he met Émilie, he was still a little bit in trouble, having just returned from exile in England, where he learned about Newton's philosophies. Soon, Émilie, her husband, and her lover Voltaire decided to hole up at her country home called Céret. Émilie wrote a friend, quote, "There is heroism, or perhaps madness, in my shutting myself up at Céret with the 3 of us." Émilie du Châtelet and Voltaire then created an Academy of Sciences with over 21,000 books, larger than most universities at the time. In 1738, they started to collaborate on a book on Newton, where Émilie did most of the math and Voltaire wrote most of the prose. Or as he put it to a friend, Madame du Châtelet had her part in the work, in that she dictated and I wrote. Of course, all of Émilie du Châtelet's work did not induce Voltaire to include her name in the title, although he did dedicate it to her and put her topless image inside the cover as an angel. After the publication of that book, Voltaire started to work on a competition about the nature of fire and light, which Émilie du Châtelet thought was dead wrong. Frustrated with Voltaire ignoring her ideas, Émilie secretly wrote her own paper. She determined that if a ray of light had any mass at all, then the speed of light would mean that, quote, an instant of light would, quote, destroy all the universe, and therefore light must have no mass. Émilie du Châtelet also decided that fire, i.e. heat, was, quote, the cause of the internal motion of the particles of all bodies. And she even predicted the 3rd law of thermodynamics 200 years before Walther Nernst, saying it was impossible that had a particle that was in, quote, perfect repose, and that, quote, all in nature is in perpetual oscillations of dilation and contraction caused by the action of fire. Neither Voltaire nor Émilie du Châtelet won the contest, nor even got honorable mention, but her reputation as a serious scientist was made. Her gossipy neighbor wrote, "I read the dissertation on fire that Madame wrote. It is so clear, so precise. I apologize to Monsieur de Voltaire, but it's much better than his. And when did she write this discourse? At night, because she was hiding from Voltaire." While researching how destructive sunlight could be if it had mass, she started to study what different scientists said about the destructive effect of moving objects with mass. And having just written a book on Newton, she was up to date on Newton's theories. However, despite what I was told in school, Newton never wrote that force equals mass times acceleration. In fact, the closest he ever came to it was, quote, a change in motion is proportional to motive force impressed. Instead, Newton and the French scientist Descartes were much more focused on the mass times the speed, as if 2 objects collide with identical mass times speed and stuck to each other, they would stop moving. And for this reason, some people started to call mass times speed the dead force. Émilie du Châtelet wasn't limited to Newton or Descartes. See, at the time, science was a bit of a nationalistic pastime. If you were English, you needed to support Newton. If you were German, Leibniz. If you were French, Descartes, often to the exclusion of others. Émilie thought this was ridiculous and wrote, "About a book of physics, one must ask if it is good, not if the author is English, German, or French." Or as Voltaire put it, quote, "In the kingdom of Madame du Châtelet, there is an absolute freedom of conscience." In 1738 or so, Emily du Châtelet learned that Newton's rival, Gottfried Leibniz, had proposed something that he called the living force that was dependent on the mass times the velocity squared, which was conserved when objects bounced off each other. Living because this quote-unquote force was only conserved for moving objects. Newton and Leibniz were enemies from their days where they argued about who discovered calculus, and almost everyone in Europe was firmly in one camp or the other. However, Emily felt differently, telling her son, quote, "Do not carry respect for the greatest men to the point of idolatry. No book is so good that one might not improve it." Now, one of the definitive experiments that convinced Emily du Châtelet that the damage of a moving object depended on the speed squared times the mass, or the living force, is dramatized by the 2005 documentary Einstein's Big Idea.
Grafsond in Leiden has been dropping lead balls into a pan of clay.
Dropping lead balls into clay, how very imaginative.
Using Newton's formulas, Monsieur Voltaire, he then drops a second ball from a higher height, calculated to exactly double the speed of the first ball on impact. So, Monsieur, care for a little wager? Newton tells us that by doubling the speed of the ball, we will double the distance it travels into the clay. Leibniz asks us to square that speed. If he is correct, the ball will travel not 2, but 4 times as far. So, who is correct?
Monsieur, I feel Mr. Newton's reputation dwindling ever so slightly.
Oh, mon père, do not succumb to her. There is no earthly reason to ascribe hidden forces to this Dutchman's lead balls.
Well, the ball travels 4 times further.
Anyway, in 1740, Emily du Châtelet published a book called Lessons in Physics, which was the first to champion Newton's theories and the idea of a living force, and helped promote both Newton's and Leibniz's theories in France, Germany, and even England. Du Châtelet continued to research science, and in 1747 she completed her magnum opus, the first and still gold standard French translation of Newton's Principia, with footnotes about the living force. Tragically, she died just before its publication at age 42 from complications from childbirth. After her death, Emily du Châtelet's ideas about Newton, Leibniz, fire, light, philosophy, and living forces were all reproduced, sometimes plagiarized word for word, by her friend Diderot in the very influential French encyclopedia. Her influence was obscured by her death, but her scientific ideas flourished. Fast forward to England in 1807. That was when a doctor and scientist named Thomas Young, who is famous for his double slit experiment from a few years earlier that demonstrated that light acts like a wave, was asked to give a series of lectures on the current state of science. Young decided to make his lectures as simple as possible because he wanted to dedicate it to the women in the audience, specifically because he felt the upper class women would be better served if they spent their time in the, quote, acquisition of knowledge instead of wasting their time than insipid consumption of superfluous time. Anyway, in his 5th lecture out of 60, he decided to rename the living force, or the mass times speed squared, saying that, quote, the living force is somewhat more concisely expressed by the term energy. His lectures were published as a book, and soon his simplified physics for the ladies caught on in England, and the term energy was used instead of living force, at least in England. Now we go back to France, and 2 ex-soldiers, Sadi Carnot and Gaspard Gustave Coriolis, who were interested in the efficiency of machines. As Carnot put it, quote, the study of engines is of the greatest interest as their importance is enormous, and they seem destined to produce a great revolution in the civilized world. Both men were the children of generals, and both men in the early 1800s went to the same school to study engineering for military officers. However, Sadi Carnot started in a much better position in French society, as he was the son of one of Napoleon's top captains, and Coriolis was the son of the former king's top captains and King Louis had been decapitated when Coriolis was just an infant. They switched social positions in 1815 when Napoleon was defeated and Carnot's father was exiled. Sadi Carnot was allowed to remain in France, but he found military life very frustrating without any political power. And in 1818, Carnot left the military and holed up in his brother's apartment in Paris, secretively studying science. Carnot wouldn't even tell his brother what he was working on. Meanwhile, Coriolis' father died, and Coriolis left the military so that he can make a little bit more money as a scientist studying engineering systems. As a former engineer, he had a lot more technical experience with actual engines than the typical academic. In 1829, Coriolis published a book on the physics of machines. In this book, Coriolis defined a new term that he called work, that he defined as the force times the distance in the direction of motion. Surprisingly, this is still the modern physics definition of work. Moreover, with this new definition of work, Coriolis used calculus and found that if an object was pushed on a flat surface, the object would have a change in 1/2 the mass times speed squared. Coriolis therefore decided to make what he called a slight modification to the definition of living force and define it as 1/2 mv squared instead of mv squared to add, quote, simplicity to the principles. He then found that if you had a machine that pushed an object up a hill, then the work minus the weight times the height equaled the change in living force. In other words, the work equals the change in kinetic energy plus the change in potential energy due to gravity. If this sounds like what you learned in high school, you're right. The only thing missing is heat. Now we go back to Carnot hiding out in his brother's apartment. In 1824, Carnot decided to publish his theories about heat engines and heat. In this pamphlet, Carnot assumed that heat comes from hot objects and goes to cold objects, and the bigger temperature difference, the more efficient the engine. All things we think true today. Carnot also came up with an idealized engine that is most efficient, that is currently called the Carnot engine. But then he made a mistake. He wrote that, quote, the production of power is not due to an actual consumption of heat, but to its transportation from a warm body to a cold body. In other words, Carnot thought that an engine absorbed as much heat as it emitted, and it was only the movement of heat that caused the engine to do work. The idea that heat is a fluid that you cannot destroy or create was called the caloric theory and was very popular in France at the time. Over the years, Carnot started to rethink his idea that heat is an indestructible fluid. He wrote in his notebook, heat is simply a movement among the particles of bodies. Wherever there is a destruction of motive power, there is at the same time production of heat in quantity exactly proportional to the quantity of motive power destroyed. Reciprocally, whenever there is a destruction of heat, there is a production of motive power. Tragically, before he could publish these thoughts, Sadi Carnot died of cholera at age 36. And these thoughts were only published in 1890, years after others gained fame for its discovery. Very few people read Carnot's book while he was alive. But 2 years after his death, another Frenchman and engineer named Paul Clapeyron based his book on heat engines on Carnot's book, which slowly gained popularity. Whew, that's a lot of people and ideas. Let's do a little recap. In 1747, Émilie du Châtelet combined the ideas of conserving living force, mv squared, with Newton's ideas, and her theories were plagiarized, memorialized in the French Encyclopedia of 1751. In 1807, Thomas Young calls the living force energy to make it easier for the ladies. In 1824, Carnot published his book on heat and is ignored for 10 years. In 1829, Coriolis defined work as force times distance and redefined the living force, i.e. the kinetic energy, as 1/2 mv squared. In 1834, Clapeyron published his thoughts on Carnot's work, including the idea that heat flows from hot to cold and the erroneous idea that heat is indestructible. Now we move back to England and a young brewer named James Joule. In 1840, 22-year-old Joule decided to systematically study if an electric motor would be more efficient than a steam engine in his bottling factory. Joule then found the equation for the amount of heat that a resistor will produce as a function of the current through it, an equation we still use today. Joule also studied how much chemical energy came from the battery and was surprised to find them equivalent. He then became obsessed with the science of heat and started building elaborate and astonishingly precise devices where falling weights would drive a spinning paddle, which would then increase the temperature of the water to demonstrate the relationship between work and heat. By 1843, Joule was trying to convince anyone and everyone that, quote, wherever mechanical force is expended, an exact equivalent of heat is always obtained. But Joule was not a professor. He was just a lowly brewer, and most people didn't listen to him. He kept on talking though. In 1847, he gave a talk at Oxford where he greatly impressed the audience, including a 23-year-old Scottish math and physics phenomenon named William Thomson. Thomson was impressed with Joule's experiments, but he didn't initially agree with his conclusions. See, Thomson had read Clapeyron's book about Carnot and was a huge fan of Carnot and Carnot's theories. He therefore thought that in order to like Carnot, you had to believe in the indestructibility of heat. Thomson decided that Carnot's theories were a good theoretical basis for creating an absolute temperature scale and became the first person to correctly get that absolute zero is 273 degrees Celsius below freezing. By the way, Thomson was knighted 44 years later and became known as Lord Kelvin, which is why the absolute temperature scale is measured in kelvins in his honor. Anyway, in this paper of 1848, Thomson mirrored what he thought were Carnot's theory about the caloric, saying, quote, the source of power is not in any absorption and conversion of heat, but merely in a transmission of heat. Although Thomson did add in a footnote that, quote, Mr. Joule of Manchester made some very remarkable discoveries, which led to a contrary opinion in heat. This paper made Carnot's theories instantly and internationally famous. In addition, Joule was delighted to have a real scientist mention him, even in a footnote, and they started a correspondence which led to a fruitful collaboration. Eventually, Joule became a famous professor, and the units of energy are called joules in his honor. Meanwhile, back in January of 1849, Thomson wrote another paper, this one only about Carnot's theories. It was this paper that led to the last scientist on our list, a quiet German named Rudolf Clausius. Clausius was born in 1822 and was the youngest of 18 children. Yep, I said that right, 18. When Clausius was 21, his family ran out of money, probably all those kids, and he had to drop out of school and become a high school teacher and get his PhD while he taught high school. He remained a devoted teacher his entire life and continued to teach even on his deathbed. When 26-year-old Clausius read Thomson's papers, he was intrigued and felt like it might be a way to make his name and get out of teaching high school. Like Émilie du Châtelet over 100 years before, Clausius took what seemed like desperate and opposing ideas and elegantly meshed them together. In 1850, Clausius came up with a new theory that was, quote, opposed not to the real fundamental principles of Carnot, but to the addition, no heat is lost. Clausius wrote that Carnot's theories and the idea that heat is a form of energy that can be destroyed or created, quote, may not only exist together, but that they mutually support each other. And Clausius included a new idea that he called interior work, but we now call internal energy, which he gave the letter U. In fact, one of the modern forms of the first law, that the change in internal energy equals the heat added minus the work done by an object, is exactly how Clausius put it, with the same sign conventions and the same letters used. With this paper, Clausius made his mark on the scientific world and finally got a job as a professor. Meanwhile, Thomson said that he independently realized that Clausius was right and that heat is not conserved, but energy is. Between 1851 and 1855, Thomson published a series of papers on the nature and mathematics of heat and energy transfer. In these papers, Thomson used the term energy instead of living force, and in 1852, Thomson divided energy into two types, statical and dynamical, which is very good etymology in my humble opinion. However, another Scottish scientist named William Rankine named it potential and actual in 1853, and Thomson renamed it potential and kinetic in 1855, the names we are stuck with today. Although Clausius had innumerable petty arguments with Thomson, he agreed that the name energy was appropriate as, quote, an abbreviated mode of expression. And by 1865, Clausius had formed the first law to be, quote, the energy of the universe is constant. As Richard Feynman said, quote, conservation of energy is a most abstract idea because it is not a description of a mechanism or anything concrete. It's just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. But as a mathematical trick, it sure is powerful. In 1881, Thomson wrote, quote, the very name energy, first used in its present sense by Dr. Thomas Young, is now a principle pervading all nature and guiding the investigator in every field of science. Back to Clausius. Clausius wasn't done yet. And in 1854, he came up with a new second law, which had to do with the heat divided by the temperature. Clausius stated that for a perfect reversible cycle, the heat divided by the temperature for the full cycle would add to 0, and for anything else, this quantity would be positive. In 1865, Clausius renamed this function entropy. But what is entropy? What does it mean? Why did he name it that? And what does it mean about our universe? Well, that is next time on The Lightning Tamers. Thanks for watching my video. Sorry it turned out so long. It just kept on multiplying with more people and more stories. If you like this one, you'll extra like my other ones because they're shorter, involve less people. Check them out. If you like my videos, why don't you subscribe? Give a thumbs up, share it on social media, all that jazz. If you really liked it, why don't you consider becoming a patron? And then you get to see the videos a day early, and you get extra special videos, and you just learn that you're a wonderful person. Big thank you to my patrons who supported me. I really appreciate it. Have a nice day. Bye. Consumption of superfluous. I can't say that frickin'. I can't say that word.